Hi again, welcome back. In today's lecture, we're going to talk about the binomial distribution. So last time we talked about the normal distribution. And so to start out, what we're going to do is we're going to compare and contrast the binomial distribution with the normal distribution. So let's start off with talking about the normal distribution. So that's the distribution we've been looking at, and it is our normal curve, kind of a bell-shaped curve. And if I drew that better, it would be a very smooth curve. And the reason why is because there is a line, an x value or a z value, for every single possible value, from negative infinity to positive infinity. So the value 1.0764328, that is a value on the normal distribution, as well as any other infinitely many values that there are. So the normal distribution is continuous. So fractions, decimals, it has it all. The normal distribution is generally made up of measurements. So that is anything that you would need a measurement instrument to measure. So something like weight or height or time or temperature or something like test scores. So all of those things are things that require a measurement instrument. So weight requires a scale. Height requires a ruler or a tape measure or something like that. Time, a stopwatch or a clock. Temperature, a thermometer. Test scores require a test. A test is a type of measurement instrument. And with all of those things, we have fractional or decimal units. So there are examples in the homework. There's one that's something about the weight of a chicken. So, that could be in fractions of a pound or an ounce, whatever is used to weigh that. Height, someone could be 6.1 inches tall or 5.9 inches tall or something like that. So decimals, fractions, all of those work with the normal distribution. So our values can be whole numbers, fractions, or decimals. All of those are just fine. For the normal distribution, if we see something like the probability that x is greater than 5, that is essentially the same. It's not exactly the same, but it is essentially the same as the probability that x is greater. Oops. Let's erase that real quick. It is essentially the same as the probability that x is greater than or equal to 5. So we'll treat these as the same. Of course, mathematically, they are not the same, but they are the same to an infinite number of decimal places. So again, not exactly the same, but for as accurate as we need to be, they are essentially the same. Because x greater than 5, if we have an infinite number of numbers that we can choose from, the number slightly larger than 5 is 5.000, an infinite number of zeros, and then a 1 somewhere down the line. That is larger than 5. And that is so infinitely close to x greater than or equal to 5 that we can treat them as the same. So when you're working on homework problems with the normal distribution, if it said something about there's one about the weight of a peanut butter jar. So the weight of peanut butter jars that is less than 16 ounces. To the number of decimal points that we're going to use, you would get the exact same answer as if I had said the probability of less than or equal to 16 ounces. It would be the exact same to the number of decimal points that we're going to use. All right, so that's the normal distribution. All right, so then we have the binomial distribution. The binomial distribution is discrete. And what it looks like, I'm going to draw a terrible picture. I'm going to show you a much better picture here in a minute. The binomial distribution, everything is kind of this stair-step thing because it's discrete. So we can only use whole number values. So the binomial distribution are counts. So we're just counting the number of things that we're counting. So if it said how many blue marbles are in a box, we could have 1, we could have 2, we could have 3. We couldn't have 3.5. That wouldn't make any sense. So the binomial distribution, the values are whole numbers only. Okay. For the binomial distribution, if we have something like the probability that x is greater than 5, that is very different than the probability, that x is greater than or equal to 5. Okay, and the reason why is because we're counting by whole numbers now. So if I say the probability that x is greater than 5, that is actually the exact same thing as the probability that x is greater than or equal to 6. Because if we think about it, the first thing bigger than 5, if we only have whole numbers, is 6. Okay, and I've got a little picture here to help us with that. So here's our blue marbles. So if I said greater than 5 blue marbles, well, greater than 5, none of these fit, right? 1 through 5, none of those fit greater than 5. So what does fit greater than 5? Well, 6 or more. In this case, I only made 8. But so the probability that x is greater than 5 is the exact same thing as the probability that x is greater than or equal to 6. And this is, it'll be a little confusing. There's going to be some times where this makes things a little harder, but it's really important to remember that we are counting by whole numbers only. Okay. All right, so now let's jump into how to work some binomial distribution problems. Let's look at an actual picture of a binomial distribution. This one looks a little bit better than my terrible drawing. So this is a distribution of, if I scroll all the way this way, you can see it goes all the way to 30. But this is, if we were to flip a coin 30 times, the probability of each number of heads. So we have the probability of 0 heads. So I wrote these up here. Probability of 0 heads to 4 decimal places is 0, as are a number of the others. As we go up, the probability of 15 heads, the most likely, if you're going to toss a coin 30 times, the probability of 15 heads is 0.1445, or in other words, there's about a 14.5% chance that if you toss a coin 30 times, you'll get exactly 15 heads. So I've got all of these written out. All of these you can see up here. This is the function in Excel that is very much like our Binome PDF function in the calculator. So very, very similar between Excel and our calculator. But anyway, so what we want to be able to do is we want to be able to find each of these probabilities. So the probability of each of these things individually happening, or sometimes the probability of a group of them happening. But real quick, let's look at the graph. So what we notice about this, another thing that we notice about this that is very different from the normal distribution, is it doesn't continue for infinity in both directions. It has a very distinct starting point and a very distinct ending point. Because if we're counting the number of coin flips that result in heads, if we're tossing the coin 30 times, then 0 is the smallest number of heads. It can't get any smaller than that. And 30 is the largest number of heads. It can't get any larger than that. If we're tossing a coin 30 times, we can't get 31 heads. So it's somewhere between 0 and 30 and whole numbers only. We can't get 13.5 heads or 20.25 heads. It has to be a whole number. So that's why our distribution is a bunch of these bars rather than a nice smooth distribution like the normal distribution is. Okay. All right. So now let's do a couple examples to see how we can calculate these probabilities. All right. So first, let's find the probability of exactly 13 heads. So that's the red bar on our screen right now, and you can see what the answer is. I've got it here on the screen, but we'll find it on the calculator. All right, so hopefully you have your distributions calculator functions from our last video. We're going to continue working on those, so if you don't have those, pause this video, go grab your notebook, and if you didn't write those down the first time, go ahead and pause the video and write these down now. These were our two functions from the normal distribution. We're going to have two more functions for the binomial distribution. So let's go ahead and write out the first one of those. So the first one is going to be the Binome PDF function. So PDF stands for probability density function, and probability is singular. So the P in there is singular. So Binome PDF finds exactly X successes. Okay, so if we want to find an exact number of successes, which is what we're doing here, we want to find... There we are. We want to find exactly 13 successes. Now, one of the things about the binomial distribution is we always have a probability of success and a probability of failure. Don't let those connotations throw you off. Success does not mean it's a good thing. Failure does not mean it's a bad thing. In this case, there's no reason why a head is a success and tails is a failure. It's just however we define the problem. So when you're reading through homework questions, if it seems like it's a bad thing or an undesirable thing that happens, that has nothing to do with how you're going to decide what success and failure is. Success is just the outcome of interest. Failure is any other outcome other than the outcome of interest. And there's only ever two outcomes in a binomial distribution. In this case, it's heads and tails. That's pretty easy because there's only two options anyway. But for example, we could use a die. I could roll a die and say, let's say 6 times. And we want to count how many times it's a 3. Well, in that, there's still only two outcomes. There's either it is a 3 or it's not a 3. And so we're grouping everything that's not a 3 into one category of not the event of interest, and then 3 as the event of interest. So anyway, so for the binomial distribution, that's where the bi comes from. Always two outcomes, either the thing we want or the other thing. All right, so let's go back to our notes for our calculator functions. So our Binome PDF function finds exactly X successes. All right, so Binome PDF. All right, so our inputs for the Binome PDF is first the number of trials. And that's just the number of times we're going to repeat the experiment. So in our example that we're doing right now with tossing the coin 30 times, that's the number of trials, 30. The second entry is the probability of success. So that is the probability of success for one trial. Not for a number of trials, but for just one trial. So when we're looking for the probability of getting 13 heads, that probability is not what goes here. That's what we're trying to find. The probability of success for one trial in our example would be 1/2 or 50%. That's the probability of flipping a coin and getting heads. And then the last number is the number of successes desired. Okay, and so the trials, we call that N, the number of trials. The probability of success, we call that P, and then the number of successes, we call that X. So it's Binome PDF N, P, and X. So those are the three inputs for the Binome PDF function. All right, so let's go to our distribution, and let's write this out. So we've got Binome PDF. Our number of trials is 30 because we're tossing a coin 30 times. Our probability of success is 1/2 or 0.5. You can put either into the calculator. It doesn't matter. And then the number of successes we're desiring, that's 13. That's the number of heads we're looking for. So 13. All right, so we'll grab our calculator and type that in. So to get to the Binome PDF, we'll press second and then the vars button to get to distributions. The first couple are normal distribution functions. The quickest way is to go up to Binome PDF. If you have a newer calculator, it's going to give you the menu option for trials, P, and the X value. If you have an older calculator, you'll type it in with a comma like I have it written on the screen. So number of trials, that's 30. The P value, that's 0.5. And the X value, that's 13. So we have 30 trials. Probability of success on any individual trial is 50%. And then the number of successful trials we want is 13. All right, so we press paste, and we'll get what you would type in if you have an older calculator, and then enter. And what we get is 0.1115, which of course was the same answer that Excel gave me when I made this table. All right, so the Binome PDF ones are the easier ones, because when we're looking for exactly a number, then we just use that number, and that's it. That's all we have to worry about. Now, what if we wanted to find the probability that X is greater than or equal to 17? So that's 17 or more successes, or 17 or more heads in this example. All right, so you could do this a very long way by using the Binome PDF function. You actually never need the second function, but it's really tedious if you would want to do it this way. You could first find the probability of exactly 17 successes, and then the probability of exactly 18 successes, and then 19, and then 20, and 21, and 22, 23, 24, 25, all the way up through 30. And then you could add all of those probabilities together, and that would give you the right answer. That would take a while. We don't want to do that. So instead, we're going to use a different function. All right, so our next function is the Binome CDF function. So CDF, that is cumulative density function. So cumulative means to sum up. So this function is going to sum up multiple probabilities. Okay. All right, so our entries here are very similar. Trials, N. Probability of success for one trial, P. The only thing that changes is what X stands for. We actually still call it X, which is admittedly a little confusing, but it stands for something different. So this is going to be the number of successes desired or fewer. And that is the really important part. So we still call that X. Number of successes desired or fewer. So it's not or greater, it's or fewer. Now, the reason why it's or fewer and not or greater is just because whoever designed the calculator designed it that way. There's no good reason. Other than that's just kind of the typical way of doing it. With our normal distribution function, we were able to put in a lower bound and an upper bound. if that was the case here with the Binomial CDF function, that would actually make it quite a bit easier. But that's not what our calculator has. So that's just not what we get to use. So instead, we're given a function that only finds the number of successes or fewer. And so we're going to have to kind of work around that a little bit sometimes to find the answers that we want. And so what we'll often have to do is find the opposite of the answer we're looking for to then help us find the answer we're looking for. Oh, and I forgot to write, so BinomialCDF finds X or fewer successes. So when you're looking for trying to figure out which function to use, Binomial PDF finds an exact number of successes. Binomial CDF finds X or fewer successes, but we can use it to find X or more successes, or we can use it to find between two numbers the number of successes. So, but the function itself only finds X or fewer successes. We just kind of have to work around that to find some of those other things. All right, so let's jump back to our distribution. So we want to find 17 or more successes. So that's anywhere between 17 and 30. All right, so let's think about here. Let's think about what we want and what we don't want. Okay, so what we want. What we want is between 17 and 30 successes. Okay, because remember, there are 30 trials here. And if we want 17 or more, then that's anywhere between 17 and 30. Okay, so now let's think about what we don't want. So what we don't want is anything else, right? So what we don't want is, so if 17 or more is what we do want, so that's all of these, all the way through 30, which is off the screen, then what we don't want is anything other than that, which is 0 through 16. It's not 0 through 17. It's 0 through 16. Okay? So we're always going to be dividing this up. So what we want is 17 through 30. What we don't want is 0 through 16. Those two things together, what we want and what we don't want, have a probability of 100% or 1. Because something has to happen, right? Somewhere between 0 and 30 successes has to happen. So either it's between 0 and 16 or it's between 17 and 30, but it has to be one of those two things. Okay, so we want to find the probability that X is greater than or equal to 17. So 17 or more successes. We don't want 0 through 16 successes. But the thing is, the Binomial CDF function won't find us the probability that X is greater than or equal to 17, not directly. But what it can find us is the probability that we get 16 or fewer successes, the opposite, the things that we don't want. So I strongly recommend, while you're first learning how to do these, always write out what is it that you want and what is it that you don't want included. It will really, really help because these can get really, really tricky. All right, so let's find what we don't want first because that's what our calculator can find us, a number or fewer. So 0 through a number, that's the only thing our calculator can find us. Can't find us a number or greater or between two numbers. All right, so this will be Binomial CDF. Number of trials is still 30. Probability of success is still 0.5. Now, our X is the number of trials or fewer that we're looking for. And again, what we're looking for is what we don't want. And what we don't want is 0 to 16. And so we're going to put a 16 here. So the most common mistake on problems like this would be to put a 17 there. And I'll show you visually why we don't want to do that here in just a sec. But first, let's find this probability. So this is the probability. This is all of these added up. So this is all of these probabilities added together. All right. So let's grab our calculator. So we go to second and then distributions up to Binomial CDF. Oops, one too many. Number of trials is 30. Probability of success, 0.5. And our x value, again, that's the number of successes or fewer when we're using the BinomialCDF function. So that's going to be 16. Again, we're looking for 17 or more. So we're finding the opposite. And the opposite of 17 or more is not 17 or less. The opposite of 17 and more is 16 or less. All right, so we'll hit paste and then enter, and we get 0.7076, so forth and so on. So 0.7077 rounded to 4 decimal places. That's what we don't want. Okay? Now, because we know the probabilities have to add up to 100%, we can then use that to find what we do want by just subtracting 1 minus that number, 0.7077. We can do that really easily on our calculator. We can do 1 minus, and then just pull our answer by pressing second and then the negative button. And so we get about 0.2923. So if the probability of getting somewhere between 0 and 16 heads, which is what we don't want, is 0.7077, then the probability of getting 17 or more heads has to be 0.2923, because those two numbers add up to give us 1. All right, so the reason why we didn't want to use 17 as our x value is because if we included 17, that would be all of these numbers. That would find us 0 through 17. And then when we subtract that from 1, we would be subtracting out all of this. We're saying this is what we don't want. And then this is what we do want. And that's not true, because we would be subtracting out 17. We would be taking 17 out, which leaves us with 18 or more, which is not what we wanted. Okay? So remember, the thing that's being subtracted, this part right here, are the things we don't want. Make sure when you are subtracting out the things you do not want to include. Don't subtract out anything that you do want to include. Okay? All right. Let's do another example. This one between two numbers. All right. So on this one, we want to find the probability that 11 is less than x, which is less than or equal to 15. Okay. All right. So what that really tells us is that we just want our number of successes or our number of heads to be between 12 and 15. Because if we say greater than 11 has to start with 12, because again, we're dealing with only whole numbers here. So greater than 11 starts with 12. And then less than or equal to 15, that does include 15. All right, so let's write out what we want and what we don't want. So we want 12 through 15. What we don't want, we're going to write out two of these. We don't want 16 through 30. And we also don't want 0 through 11. Okay, so we don't want 0 through 11. We also don't want 16 through 30. We only want 12 through 15. All right, so we're going to take care of these one at a time. So we know all of this is 100%, right? So there's a couple different ways that we could do it. But the easiest way to do it is first, let's find the probability that x is less than or equal to 15. So that's all of these. So somewhere between 0 and 15. So essentially, we'd be taking out the 16 through 30. That's what we're going to be taking out first. All right, so to do that, what we're finding here, again, we're finding between 0 and 15. So the probability that x is between 0 and 15, that's 15 or fewer heads if we toss a coin 30 times. Okay, so that's going to find both 0 through 11, which we don't want, and 12 through 15, which we do want. We'll separate those out later. But first, let's find the probability that x is less than or equal to 15. And that's exactly what our calculator finds, the probability of a number of successes or fewer. All right, so to find that, everything between 0 and 15, we'll use BinomialCDF. Number of trials is still 30. Probability of success is 0.5. Number of successes is 15. So this is going to find us everything between 0 and 15. Okay? So this right here finds us 0 to 15 successes. Okay, so let's find that. All right, so second distributions, we'll go up to BinomialCDF. Trials are still 30, probability of success 0.5, x value now 15. So we're trying to find 15 or fewer. All right, so that gives us 0.5722. So 0.5722, that's the probability that we get between 0 and 15 heads. Okay, so we've taken out this part. We've taken out the probability that we get between 16 and 30 heads. So we already took care of that. So now we have 0 to 15. Now what we have left that we don't want is 0 through 11. What we want is 12 through 15. What we don't want is 0 through 11. All right, so if both of those together, 0 through 11 and 12 through 15, if that gives us 0.5722, then if we can just find the part that we don't want, 0 through 11, and subtract that out, then that gives us our answer. So remember, anytime we're subtracting, we are subtracting out what we don't want. So always write that out, what we want, what we don't want. So we don't want 0 through 11. All right, so let's find that. That's going to be BinomialCDF. 30, 0.5, and 11. Okay, so again, we don't want to put 12 there because we're going to eventually subtract this out. So we're subtracting out things we don't want. So this is finding us 0 through 11. All right, so let's find that. So second distributions up to BinomialCDF. Trials is 30, x value is, trials is 30, p is 0.5, x value 11. And we get 0.1002. All right, so what we know is that what we don't want and what we want, at least those two, so between 0 and 11, and between 12 and 15, those together, that's 57.22%, or 0.5722. So that's the blue area here and the red area here. Those two combined, 0.5722. We also know this blue area right here is 0.1002. So if we know those two things combined, or 0.5722, and we know the part we don't want is 0.1002, then we can find what we want. Let's scroll over. We can find what we want by taking 0.5722, the probability of between 0 and 15 successes, and subtracting out 0.1002, the probability of between 0 and 11 successes. So if we take between 0 and 15 successes, so that's all of these. We take all of those and we subtract out all the successes, 11 or fewer. Then that's going to leave us with just the successes 12 through 15. So subtract those two values, and that's going to give us 0.4720. So that's the probability that we get between 12 and 15 successes, or more than 11. X is more than 11 and less than or equal to 15. All right, so those are the two functions that we're going to use. Again, let's recap real quick. Binomial PDF finds an exact number of successes. That one's fairly straightforward. We just pick the number that we want. If we want a number of successes or greater, then we first have to find the number of successes or less and then subtract that from 1. So like on our example where we wanted 17 through 30. We wanted 17 through 30. We didn't want 0 through 16. So we found 0 through 16 and subtracted it from 1. Now, if we're just asked on a question to find the probability of less than a number of successes, then let's look at this one, for example. If we wanted to find the probability of less than 18 heads, so less than 18 heads, first of all, that's the same thing as saying the probability that x is less than or equal to 17. Because less than 18 really starts with 17. So that's all of these. To find that, all we would have to do is find the Binome CDF, 30, 0.5, and 17. We don't need to subtract it from 1 because we're looking in the less than direction. The less than direction is what the Binome CDF function finds. It finds a number of successes or fewer. The only time we're ever going to subtract from 1 is when we're looking for a number of successes or greater, like we were on this one. So if we wanted 17 or more successes, we had to find the opposite, something or fewer, and subtract it out. One of the biggest mistakes I see is that when some people, every time they use Binome CDF, they subtract it from 1, every single time. And that's not the way it works. If you're finding a number of successes or fewer, you just use the function. If you're finding a number of successes or greater, you want to find the opposite, what we don't want, and then you subtract that from 1 to find what you do want. All right, so that's the binomial distribution. We have our two functions, Binome PDF, there's our two functions. Binome PDF, which finds exactly x successes, and then Binome CDF, which finds x or fewer successes. All right, good luck on the homework, and I'll see you next time.